In this video, I'm going to introduce index notation specifically in the context of special relativity. Now, writing out vectors and matrices with all of their components in all of their glory all of the time requires quite a lot of writing, and it really gets quite cumbersome. And when we get to more advanced types objects, we'll find that we have mathematical objects that we can't even really write out in all of their glory, at least not very easily. And so what we're going to do instead is we're going to introduce something new called index notation. Now, I'm sure many of you have written variables with indices before, and maybe you've probably done calculations using things like the Einstein summation notation previously. But things are going to work maybe a little differently, and it might be a little more complex in special relativity than what you've seen before. So the first thing I want to mention, generally, we're going to be using Greek letters for our indices. So mu, sigma, rho, that's supposed to be a rho, delta, etc. These are going to be referred to as Lorentz indices. These are Lorentz. I don't know why I'm pointing just at that one, so I should erase that maybe. These are called Lorentz indices. And we'll see that these are going to be for objects that transform with Lorentz transformations, thus the name Lorentz indices. And these are going to run over our four spacetime coordinates. So mu runs over, often we'll write it as 0, 1, 2, and 3, where 0 is sort of representing our time coordinate, and then 1, 2, and 3 are our three spatial coordinates. Oftentimes, people will also write this as t, x, y, and z specifically, using the standard Cartesian x, y, and z. I kind of like 0, 1, 2, and 3 better because we might choose to use polar coordinates instead of Cartesian coordinates. We can use whatever spatial coordinates we like. It doesn't have to be x, y, and z. But there is going to be one sort of time-like index always. So 0, 1, 2, and 3, I have a slight preference for, but whatever you choose to use, there just needs to be 4 of them. Oftentimes, people will use Latin letters for if they just want to focus on the spatial indices. So maybe these are sort of bullet points. Sometimes people use Latin letters to represent just the spatial part. And so by Latin letters, I mean like I, J, K, right? Our regular letters, where these run over, for instance, 1, 2, and 3, or X, Y, and Z. Right, so just the spatial part of our indices, people will use Latin letters. So when we use our Greek letters, that's reminding you this is really something that runs over all of our space-time coordinates. So those are sort of standard conventions. I mentioned these things are going to work differently than the indices that you've seen before. And one of the major differences is that we're going to have something where we have upstairs versus downstairs. And these are going to be different. So what I mean by upstairs is that we have our index, say on, if A is, for instance, some 4 vector, we can write our index upstairs, and then downstairs would be a mu. These, even though they're both called A, are different objects. Their components take on different values. However, they are related to each other. I'll say there are common names for these, which are contravariant and covariant. So often this will be referred to as a contravariant vector and a covariant vector for upstairs and downstairs. I admittedly often in the past have just forgotten which one is contravariant and covariant, and it's terminology that I, as someone who doesn't remember things very well, I don't use it very much. Instead, I just sort of stick to upstairs and downstairs because I always remember what I'm talking about there. These objects are going to transform in different ways under Lorentz transformations. So they really are, it is important to realize that they are distinct objects, though they are related. When we're just doing special relativity, these two objects have a very simple relationship. So for our contravariant vector, or like I could just say our 4 vector with the upstairs index, if this has 4 components, A0, A1, that's supposed to be a 1, A2, and A3, then our covariant vector, again, just in this nice case of special relativity that we're doing, is A0, that first component doesn't change, and then we add minus signs to our spatial components. Right, so maybe I should put this in red. So we have our minus signs on our covariant version of the vector. So this is a mild difference, and we'll see that we've seen these minus signs on spatial terms coming up in the past, and this is going to be a very helpful way of keeping track of these minus signs. I'll mention we're doing special relativity here. If one day you go on to general relativity, then you'll continue to have these contravariant and covariant vectors, which again will be related, but they will differ by more than just minus signs. So as you go on to more complicated relativistic theories and a general theory of relativity, then things are going to get a little more complicated, which will make this index notation even more helpful and important. Okay, so this upstairs versus downstairs distinction is going to be key here. And again, that's probably something that's very new to you. So you're going to really have to not be sloppy about when you write something as an upstairs versus a downstairs index, because there's a very important mathematical difference. And here we're already seeing it. It's just a minus sign, but they're very important minus signs. So the other thing we'll use a lot is Einstein summation, which hopefully you've seen before. It's not too complicated. It's just sort of a notational convention. But we're going to be using it again in a slightly different way than you might have seen it before. And again, this has to do with this upstairs versus downstairs-ness. So Einstein summation simply tells us if we have a repeated index, then that means that we're summing over it. So it's just, again, it's saving us from writing sums all the time. So repeated indices are summed over. And when we have repeated indices, one always needs to be upstairs and one always needs to be downstairs. I'm going to put this in red. Note, one will be upstairs and one downstairs. You cannot have 2 repeated downstairs indices or upstairs indices, which is to say, so if we have A mu, B mu, this is what we like. We have an index which is repeated. We have these 2 mu's. One is upstairs and one is downstairs. And what this represents is the sum of mu from 0 to 3 of A mu, B mu. So when I talk about Einstein summation notation, all I'm doing is I'm saying I'm not going to write this sum because otherwise we would be writing a lot of sums all of the time. So it's really just a shorthand. We aren't doing anything fancy here. We're just using a notational convention, which is quite convenient. You never want, so A mu, B mu, like I don't even want to write this. This is bad because those are both downstairs. You will never, this is a meaningless mathematical object that you should never write. Similarly, A mu, B mu, that's bad, right? We'll never have anything that looks like that. The only thing that we can have that looks kind of like that, and more on this later, is eventually we'll talk about adding things. So this is okay. And this is not summed over, I'll mention. This is good. And there's no sum here. I mean, there is a sum because I'm adding two vectors, but no Einstein summation convention. So when we're using Einstein summation, it's within a particular term in your expression. And I think as we do this more, that will become clearer. So let's actually just do sort of an example using this. So let's calculate. If A mu is A0, A1, A2, A3. We've learned A mu downstairs is A0 minus A1 minus A2 minus A3. And then let's say we have some other vector, B mu. Then A mu, B mu. Or it doesn't really matter, but let me do this instead. Here, again, this represents the sum from 0 to 3 of A mu, B mu. And this is A0, B0 minus A1, B1 minus A2, B2 minus A3, B3. And we see that this is our dot product of four vectors. All right, so this is where I'm saying keeping track of our upstairs versus downstairs indices and using this Einstein summation is a nice way of writing out this dot product thing that we defined previously, but now we can just write this and we know that that's what we mean. And of course we could do things like a mu, dotting a vector with itself. And of course this is A0 squared minus A1 squared minus A2 squared minus A3 squared. It's important here. Hopefully what I'm writing is clear because here I have this A upper index 0, 1, 2, and 3, which is different than the squared. Some of those things are just a little bit confusing, and you just have to keep track. So that's how we're using index notation for sort of some of our simplest objects, which are just our vectors. We can also use it for slightly more complicated objects, which are known as tensors. Our four vectors are actually just an example of a tensor. So these are simply objects with one or more Lorentz index. And we name them or we distinguish them by something known as their rank. So their rank is the number of Lorentz indices they have. So for example, 4 vectors are rank 1 tensors. And that's because they have just one Lorentz index, right? These objects, these A's and B's that I was just writing down that represent our 4 vectors, we just have one index. So these are known as rank 1 tensors. But we're going to be very interested in more complicated objects that have 2 or more Lorentz indices. I'll say in special relativity, we'll mostly be focused on either rank 1 or rank 2 tensors, and we won't really go too much beyond that. Again, if you go on to general relativity, then things get a little more complicated and you'll deal with. Like the Riemann tensor is a rank 4 tensor, so this is a 4 index object. So it gets very complicated, but we will not, that is for general relativity. Here we're sticking strictly to special relativity. So we could talk about rank 2 tensors, which is sort of the next step up from our 4 vectors that we were dealing with. So these, for example, look like T mu nu or T mu nu, or we could have one up and one down. And it's important to note that this is different than T mu nu. So you have to, not only are we really being careful about whether indices are up or down, notice here, the mu is to the left of the nu. And then in this case, that's also true. So, but which one is up and down and whether it's right or to the left is important, right? We do not generally want to write, or not generally, we never want to write T mu nu, where they're one right on top of each other. Because in general, these 4 objects are going to be related to each other. That's why I gave them the same name, but they are not the same object. We'll see that they're different objects in a similar way as A mu with an upstairs is different from A mu with a downstairs. These 4 objects are going to be related, but slightly different. And again, in special relativity, those differences are really just going to be keeping track of minus signs in general. But those minus signs are physical and important, and you're going to mess things up if you get it wrong. And that's rank 2 tensors. So I guess I'll just for completeness, we could also talk about some examples of rank 3 tensors. This might be T mu nu rho, or T mu nu where the row is downstairs, etc. Right, those are objects with 3 Lorentz indices. Okay, so that's writing objects with Lorentz indices, which we refer to as tensors. We'll see in future videos how we're going to actually do calculations with them, but that's sort of a basic introduction to these objects. One thing I want to say, rank 2 tensors can often, we can write them as matrices. And generally, but this is sort of a convention. The first index, which is the one to the left, is going to be the row, and the second one is going to be the column if you write it as a matrix. Early on, that might be a little bit of a helpful thing to do to write things as matrices because matrices are things that you're sort of familiar with and they feel tangible to you. Ultimately, we're going to want to move away from that a little bit. So rank 3 tensors, you obviously can't easily write out as a matrix. It's also when we start to do things like we're multiplying tensors together or adding them together, I mean, mostly multiplying together, writing things out as matrices can get a little confusing because when you multiply matrices together, the order in which they're written matters. But often when we write expressions with products of tensors, it doesn't matter the order. And you have to be really careful in thinking about the Einstein summation that's going on to think about how things should be multiplied together if you were to write it out as a matrix. So we can do that, and we will do that a little bit. And so it's sort of okay to think of these tensors as being represented by matrices because there's something that's familiar, but just be careful. So for now, I'll just say just be careful about that because it's easy to mess yourself up if you try to do that too much. All right, so that's the basics of index notation. So really, we're just writing objects with indices here. Thanks.